Episode 25, Establish Secure Architecture and Foundational Design Choices, we focus on anchoring systems on trustworthy patterns before a single line of code is written. Early architecture work shapes everything that follows, from how teams design interfaces to how they handle incidents in production. When foundational decisions are made thoughtfully, you avoid fragile add-ons later and instead build environments that are secure by construction. This is the moment where you define the guardrails, defaults, and assumptions that will quietly govern every design discussion and technical choice. Treating architecture as a first-class security discipline ensures that resilience and clarity are built in, not patched on. To start, you need to define architectural goals that balance security, performance, reliability, and operability in realistic ways. Security cannot be isolated from the other dimensions. It must coexist with latency expectations, throughput requirements, uptime targets, and operational workloads. These goals help you articulate trade-offs, such as accepting a slight performance cost for stronger cryptographic protections or adding operational tooling to reduce incident resolution time. When these goals are explicit, teams have a shared frame of reference for evaluating designs and understanding why certain choices carry more weight. Clear goals prevent teams from optimizing one dimension at the silent expense of another. With goals articulated, you can select reference architectures that align with your risks, constraints, and organizational capabilities. A reference architecture might describe a layered model, an event-driven approach, or a microservices pattern, each with known strengths and predictable weaknesses. You want a pattern that your teams can operate confidently, not just one that looks modern or elegant on paper. Constraints such as compliance boundaries, resource limitations, or legacy dependencies should guide this choice, as should an honest assessment of talent, tooling, and operational maturity. When the chosen architecture fits your reality, future designs become more consistent and maintainable. Once the overall structure is chosen, you segment trust zones, interfaces, and control points with boundaries that enforce different expectations. Trust zones define where more sensitive operations occur, separating internal services from public-facing interfaces or administrative management layers. Interfaces mark the points where data moves between these zones, and they should be designed with explicit checks, transformations, or validations. Control points, such as gateways, proxies, or service meshes, provide enforcement, monitoring, and logging opportunities. When these boundaries are explicit and respected, they limit the blast radius of failures and attacks while simplifying review and oversight. Identity, policy, and telemetry work best when centralized as shared platform services instead of fragmented across teams. A centralized identity service ensures that authentication, authorization, and session logic follow a consistent pattern, reducing the risk of bespoke flaws. Centralized policy services allow rules about access, routing, or data flow to be defined once and applied everywhere, improving control and reducing duplication. Telemetry platforms collect logs, metrics, and traces in a unified format, making it easier to detect anomalies and correlate events across systems. When these services are shared, teams focus on business logic rather than reinventing foundational security building blocks. Cryptography is too important to improvise, so secure architecture efforts must standardize cryptographic choices, key life cycles, and secret distribution methods. Standardization ensures that teams avoid weak algorithms or ad hoc implementations that might pass tests today but fail in the future. Key life cycles describe how keys are generated, rotated, stored, and eventually retired, aligning with both security and compliance expectations. Protected secret distribution methods use vault services, hardware security modules, or sealed storage to prevent sensitive material from leaking into code repositories or logs. These choices create a consistent cryptographic baseline that can be evaluated and improved over time. Privacy-preserving data flows reinforce the commitment to limit exposure and reduce harm from inevitable failures. Minimization ensures that only necessary data is collected and stored, which reduces both risk and operational overhead. Tokenization can substitute sensitive elements with controlled references, allowing many operations to occur without direct access to personal or regulated data. Aggregation techniques can allow analytics to function without exposing raw logs or granular identifiers. When privacy is embedded into data flows early, you avoid complex retrofits and reduce the scope of incidents when something goes wrong. Secure communication patterns must also be defined at an architectural level so that teams do not reinvent them under pressure. Mutual Transport Layer Security, often called MTLS, ensures both ends of a communication channel authenticate each other, not just one side. Message signing adds integrity, guarantees that persist even after the message leaves the channel, protecting against tampering. Replay protections enforce freshness by rejecting old or duplicated exchanges, reducing opportunities for intercepted traffic to be reused. Rotation schedules for certificates, keys, and tokens maintain long-term security and limit the usefulness of compromised credentials. These patterns anchor trust across distributed systems. Resilience planning brings reliability and security principles together by defining how systems behave when stress or failure appears. Redundancy allows components to fail without taking the whole system down, while circuit breakers prevent cascading failures by cutting off unhealthy dependencies. Backpressure mechanisms slow or reject excess traffic when downstream services are overloaded, protecting both performance and stability. Graceful degradation techniques ensure that essential functions remain available even when optional features are temporarily disabled. These methods help systems recover quickly and maintain consistent behavior during disruption. Observability is a cornerstone of secure architecture, and it begins with preparing structured logs, traces, and metrics supported by tamper-evident storage. Structured logs make it easier to search, parse, and correlate events without relying on brittle pattern matching. Distributed traces provide visibility into how requests move across services, revealing bottlenecks and unexpected behavior. Metrics create lightweight signals that can trigger alerts or indicate trends in performance and security health. Tamper-evident storage, whether through integrity checks or trusted platforms, ensures you can trust the data when an investigation truly matters. Observability is what turns architecture into something you can actually understand and operate. To keep architecture decisions durable and reviewable, it is essential to document decision records that capture context, alternatives, and measurable acceptance criteria. A decision record explains what problem was being solved, what options were evaluated, and why the chosen path made sense given constraints and goals. Acceptance criteria establish what outcomes will prove that the decision was successful, such as latency targets, access boundaries, or evidence traces. When these records exist, you can revisit architectural choices months or years later with clarity, even if the original team has moved on. They provide a starting point for evolution rather than forcing teams to rediscover history. Before any architecture is finalized, it should be validated using threat models, misuse cases, and early evidence prototypes. Threat models reveal where trust boundaries, data flows, or assumptions might create risks that need additional controls. Misuse cases show how actors, internal or external, might push the architecture into unintended behavior, uncovering areas where enforcement is too weak or assumptions are too optimistic. Early evidence prototypes, such as proof-of-concept monitoring or simplified service flows, demonstrate that key control ideas actually work in practice. Validating architecture in these ways ensures that foundational choices hold up under scrutiny rather than remaining theoretical. As you zoom out, the core elements of secure architecture form a consistent pattern. Establish goals, segment trust, centralize platform primitives, standardize cryptography, preserve privacy, plan resilience, ensure observability, and validate assumptions before committing. These themes repeat across many systems because they are rooted in predictable human and technical behaviors. When treated as reusable templates rather than custom inventions, they accelerate design reviews and reduce long-term risk. Keeping these patterns visible helps teams maintain focus on what truly matters as systems evolve. To close, translate the ideas from this episode into one practical step by drafting a quick architecture sketch for a system you know well. Capture its major zones, key services, communication paths, and critical enforcement points in a simple diagram or text outline. Then record your first decision entry, describing why one architectural choice, identity model, cryptographic baseline, or trust segmentation makes sense given current risks and goals. That entry becomes the seed of a durable architecture record. Over time, a small but consistent set of sketches and decision records will anchor your systems on strong foundations that are easier to defend, review, and evolve. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.